Welcome to this explainer. Today, we're unlocking something truly special, LTspice. Our sources call it the absolute best-kept secret in electrical engineering today, and honestly, they hit the nail right on the head. It's an incredibly powerful, totally free, open-source circuit simulator. So if you've ever pulled your hair out over the insane cost of premium software or felt totally overwhelmed by endless physical prototyping, well, you are in the exact right place.
Here's a quick look at our agenda for today. We'll cover the hidden simulation gem, building your first circuit, customizing component models, creating circuit symbols, the 4-bit calculator, and finally, why LTspice matters. We're starting with the basic theory and scaling all the way up to building a fully functional 4-bit calculator right inside the simulator. All right, let's jump right into Section 1, the hidden simulation gem.
So is the most powerful free tool for engineers actually being ignored? That really is the million-dollar question, isn't it? See, LTspice is a high-performance simulator, originally developed by Linear Technology, which is now part of Analog Devices. But despite its massive capabilities, a lot of folks just assume it has this brutal learning curve. The interface? Yeah, it can look a bit dated, which pushes people toward those expensive commercial tools. They kind of think, well, if it's free, it must be missing something, or it's just going to be way too hard to pick up. But as you'll see, that perception is literally holding a lot of talented designers back from doing their absolute best work.
At its absolute core, this is a SPICE simulator. SPICE stands for Simulation Program with Integrated Circuit Emphasis. It's a bit of a mouthful, but what does that actually mean for you? Well, it means you can design, test, and refine your circuits entirely in the virtual world. You get to see exactly how the electronics are going to behave way before you ever solder a single wire. In the fast-paced world of engineering, being able to rapidly prototype like this, it's huge. It saves vast amounts of time, resources, and, of course, money. And when you look at the sheer volume of professional features packed into this thing, it is mind-blowing that it costs literally $0. We're talking about core benefits like a massive, comprehensive component library full of passives, diodes, and op-amps. It has a wildly efficient and lightning-fast simulation engine built for complex designs, a streamlined user interface, and super advanced analysis options, DC, AC, noise, Fourier analysis, the whole shebang. Best of all, free cost. It's an absolute game changer, especially for startups, students, or hobbyists looking for professional-grade reliability without those crushing licensing fees. Okay, moving right along to Section 2, building your first circuit. A lot of people think a tool this powerful must be super clunky to use, right? Actually, it's the exact opposite. Using the streamlined schematic capture tool, you can whip up a basic circuit in literally seconds. The workflow is fantastic once you know the shortcuts. Step 1, you drop a voltage source. Step 2, place a resistor. And here's a pro tip. Just hit R to instantly grab it, and Control R to rotate it right into place. Step 3, add an LED. Step 4, pop in a ground and draw your wires. Bam, done. It flows so naturally. But here is where the simulator kind of acts like your personal tutor, teaching you real-world logic. Say you set up your circuit, run an operating point simulation, and you're looking at the results. Wait, negative current? Your resistor is backward. It's a fun little mini mystery. In a real physical circuit, a basic resistor couldn't care less which way it's facing. But in a SPICE simulation, the math absolutely cares about direction. A negative current just means your resistor is placed in the wrong direction and needs a quick 180-degree flip. It's a prime example of how the software demands precision and builds much better engineering habits. Which brings us to Section 3, customizing component models.
Here's the truly crucial point. LTspice isn't just throwing generic shapes onto a blank screen. It accurately simulates real-world physics. Let's take that LED in our simple circuit as an example. A generic default LED might show a voltage drop of around 693 millivolts. But our sources point out that is just not realistic for a standard visible LED. It really should be closer to 1.7 or 1.8 volts. With LTspice, fixing this takes 2 seconds. You just right-click, browse the massive library, and select a real-world part, like a Fairchild LED. Instantly, your simulation updates to a highly accurate 1.762 volt drop. You're modeling reality now, not just textbook theory.
But what if the library doesn't have that highly specific component you're looking for? Are you stuck?
No way! I was genuinely amazed by this. You can use a SPICE directive. This means you can literally paste custom code directly onto your schematic to modify the core physics. By tweaking underlying parameters like saturation current, you can build a totally custom component. Need a specific yellow LED with exactly a 1.938 volt drop? You got it. You can even save it into your library for future projects. That level of flexibility, it's just unmatched.
Let's keep leveling up. Section 4. Creating circuit symbols. Up to now, we've only been looking at static numbers. But to really grasp dynamic circuits, we need what's called a transient simulation. This analyzes and graphs the circuit's behavior, like changing voltages and currents, over a specific period of time. Imagine we build a full adder out of individual transistor-level NAND gates. By running a transient simulation over, say, a 1-second timeline, we can actually probe the inputs and outputs, visually graphing the exact moment those logic gates calculate that 1 + 1 = 2. How cool is that?
But let's be honest, a full adder made of raw transistors is a visual nightmare. If you try using multiple adders like that, your workspace is going to look like a spider web. Well, LTspice has an elegant fix. Step 1, delete the simulation wires. Step 2, clearly label your inputs, like A, B, and carry in. Step 3, label your outputs, sum and carry out. Finally, step 4, tell the software to open the sheet as a new symbol. It automatically packages that whole complex schematic into one clean, reusable rectangular block. And that brings us to Section 5, the 4-bit calculator.
This right here brilliantly illustrates the true scalable power of this hidden gem, because we are literally about to build a computer. By just dropping 4 of those custom full adder symbols we just made onto a brand new schematic, we've instantly built the logic for a 4-bit calculator. Think about the hierarchy going on here. Inside those clean little blocks are dozens of complex transistors. But for us, it's super easy to read. We wire up 2 4-bit inputs and route the output to 5 LEDs representing the values 1, 2, 4, 8, and 16. It is wildly exciting seeing this come together in a free tool.
And the ultimate proof is in the pudding, the simulation itself. Our sources pushed this layout to its absolute limit. They turned on all the inputs to represent the number 15, plus another 15, and activated the carry-in bit for an extra 1. The simulation runs, the logic cascades perfectly through all those hidden transistors, and boom, it correctly calculates 31. All 5 output LEDs light up beautifully in the virtual circuit, proving the logic is completely flawless without ever touching a breadboard. Finally, Section 6, why LTspice matters.
Building a virtual calculator is incredibly satisfying, for sure. But how does this translate to the messy, unpredictable physical world? Well, here is a vital reality check. Our sources simulated an astable multivibrator, basically a circuit that blinks LEDs back and forth. In LTspice, the wavelength measured exactly 1.35 seconds, but when built in the real world and measured with a physical oscilloscope, it was 1.136 seconds. It's incredibly close. It proves the massive value of rapid prototyping, but it's also a gentle reminder that physical parts have real-world tolerances and quirks. The simulation gets you 95% of the way there in record time, but real-world tweaking is always going to be part of the job.
I think our source material really hit the nail on the head with this quote. Its functionality and reliability are unmatched in the realm of free simulation software. It truly empowers you to test, fail, iterate, and succeed at the absolute speed of thought, totally unburdened by financial cost. So the capabilities are vast, the cost is literally 0, and the only real barrier is just your willingness to dive in and learn it. The question is, will you continue paying for premium software and doing things the hard way, or is it finally time to unlock this hidden gem for your next big design? Thank you so much for joining me on this explainer. Have fun and happy simulating.